Hello everyone, good morning. Okay, so let's get started with today's class. Right. So in today's lecture, we'll be looking at this topic called scheduling. Right, and in this topic of scheduling, we are going to be discussing how the OS or the algorithms that are used to do this or perform this multi-threading. All right, so when we say that we have multiple threads, all right, the OS is of course trying to manage its time across all the different threads and tasks that we create. So what is the policy? Okay, what are the different types of policy that can be implemented? Okay, and how the OS goes about making these decisions. Okay, so we're going to analyze it, okay, from the theoretical perspective, okay, how the OS is behaving, okay, and understand this concept of scheduling, right? But of course, scheduling itself is a very, very in-depth and detailed topic by itself. Okay, so that one is, if you are doing any advanced OS course in the future, you probably go more in-depth into scheduling and looking at all the algorithms and so on. All right. So in this lecture, we're going to sort of introduce you to that concept. Okay, and as usual, what we will do is at the later half, we will look at the lab demo for this week, okay, on the Semaphores. All right, and before the break, I'll also talk a bit about the midterm, right, which is next week. Okay, so just to let's get started here. Okay, so there is a instruction to the midterm and all that I've already uploaded. All right, so there's a midterm quiz prep. This is just to give you the idea or the feel of how the questions would look like in the Luminous quiz. Okay, so I think most of you are already familiar with it. Okay, most of you have done either EVP1 or EVP2 where you had the Luminous quiz, so you should be familiar with the way it operates. Okay, but if you are not, then you can just try the quiz prep just to see how the questions and everything will appear on the online platform. All right. The next thing that I wanted to show you is this, where we are right now. So if you look at it, we are in week 9. Okay, and week 13 is your final demo. Okay, that means technically you have only 4 weeks left. Okay, I keep repeating this, okay, because week 13 is not a week for you to do any work in the lab. Okay, you don't have lab access. All right, Monday to Thursday, it will be fully booked for EPP1 and their assessment. All right, and Friday is your lab. Okay, so you do not have any lab access time on week 13 at all. Okay, so you only have these 4 weeks left. Okay, to put everything together and write the hardware, write the code and so on. Okay, if your hardware is up and ready, okay, the rest of the software you can do in your own time. All right, so the important thing is make sure the hardware is integrated. All right, so you do not get stuck, not being able to test what you are doing because the hardware is not ready. Okay, so please, okay, make full use of at least this week and next week to make sure all the hardware is done. Okay, so that you can focus on the software after that. Okay, so let's get started with the lecture. Okay, so on the topic of scheduling, okay, so let's take a look back at this state transition diagram. Yeah, so this basically shows us the states of or the state in which any task can be in at any time. All right, so we sort of already have an idea that when you create a task, it goes to the ready state. Okay, and inside the ready state, your scheduler is there. All right, so when your scheduler is there, okay, you can have a list of tasks in the queue. All right, so who gets to run first? So the scheduler must look at all these tasks and make a decision on who is going to be scheduled to run next. Okay, or make use of the CPU next. Okay, once the current task frees up the CPU. So there has to be some mechanism in place. All right, some policy, some rules it has to follow to make this decision. Okay, so that is what we call the scheduling policy or scheduling algorithm. All right, and that is what we're going to be looking at. All right, so you want to make sure that we have a consistent set of rules or policy. All right, and you're able to follow this policy to make sure that all the tasks can still fulfill their deadlines. Okay, so let's look at a simple example. All right, so in this lecture, okay, we are going to again make some assumptions of how tasks behave. Okay, again, these are just assumptions to help us with the analysis. Okay, in reality, some of these assumptions may not hold true. Okay, some may still hold true. Okay, but to do the analysis, okay, we make some assumptions. So let's first look at this example. All right, so the assumption is that at time t equals to 0, all the tasks are ready at the same time. Okay, all the tasks are ready. Okay, so that means that at the time t equals 0, you have 3 tasks A, B, and C all waiting to use the CPU. All right, and let's assume that we have no policy yet and we just want to try it out. Okay, so we say that let's go by this order A, B, C. Okay, if I look at A, B, C, right, scheduled in this order, what happens? Okay, I will run A first. So A is 10 milliseconds. All right, the deadline is 50 milliseconds. So the objective is, of course, you must complete the execution of the task before the end of the deadline. All right. Now, if after that I schedule B, so A is done, then I schedule B. So B takes 20 milliseconds and the deadline is 20 milliseconds. All right. So this deadline is always with respect to t equals to 0. All right. And after that, what happens? I run C. Okay, based on this schedule here, I run C, and C's deadline is 60 milliseconds. All right. So what do you see? You see that the deadline for A, which is 50 milliseconds, no problem. I'm able to meet it. Okay, deadline for C, which is 60 milliseconds, also I'm able to meet it. But the deadline for B, I miss it. Okay, because the deadline for B is 20 milliseconds. I mean, this was the deadline here. Okay, so by 20 milliseconds from time t equals to 0, I'm supposed to have completed task B. Okay, but because I put A first, B will miss the deadline. All right, so this scheduling algorithm will not work, okay, based on my current task set that I have. Okay, let's try another example here. The same time and deadline that we have, but now I put it B first, then A, and then C. Okay, so if I go by this order, okay, what you see is I'm able to meet the deadline for B and able to meet the deadline for A as well as for C. All right, so there is no issue with running all 3 tasks, okay, without missing any deadline. Okay, so this sequence works for us. Correct. And then the last one, B, C, A. So I run B first, followed by C, and then followed by A. So in this, you see that B can meet the deadline, C can meet the deadline, but A will miss the deadline. Okay. So again, in this example, A will miss the deadline. So you can see that just by switching the order around, okay, in one case it works, but in the other 2 cases it doesn't work. Okay, so this is of course important because when you are creating a multi-threaded system that you have deadlines, all right, you want to make sure you fulfill the deadlines. All right, so this is the thing we want to look at. Okay, how do we come up with a strategy, all right, or approach to make sure we can meet the deadlines. All right, and of course this can get more complicated because right now we are basing on the thing that there are no preemptions. You know, preemptions means when task B runs, it just runs fully. Task C runs, it just runs fully. Okay, but again, that is also not something you expect in reality, right? Because of the continuous switching between the tasks, there's going to be a lot of context switching happening. All right, so that comes us to getting familiar with some terms here. So firstly, what we will say is, in our analysis, we are going to have a fixed number of tasks, okay, n number of tasks, and we're also going to make this assumption that tasks are periodic in nature. All right, so again, this may or may not hold true in reality. All right, if you like relate back to our project, all right, there are some tasks that may be periodic, all right, maybe the LED blinking, the buzzer, playing some music. So those tasks may have some periodic nature with the way it behaves. All right, but for example, the motor task, okay, motor task is not periodic because it just responds as and when you send a request over. Okay, so some tasks may be periodic, some may not. But in the analysis here, we will take it that all tasks are periodic, okay, and the periods are constant, okay, they not change. And a task can be seen in infinite sequence of instances. Okay, so when you say a task, I can run that task many sort of in multiple instances. Okay, and of course, once I release a task, okay, we say that the moment it is released, it becomes ready. Okay, so we do not say that I release the task and then it is in a block state because it's waiting for a semaphore or waiting for a mutex. No, we do not factor that in. We just say that the moment the task is available or is ready or is released, okay, then we say it is ready. I mean, it wants to use the CPU. Okay, and every instance of a task may have different execution times. Okay, as you can see, okay, in this case, okay, you have different execution times. Basically because when you write a code, okay, sometimes you may have a loop, you may have some if else. All right, so in a particular input sequence, maybe you execute the if, another input sequence you execute the else, and what you do for the if and the else may be different. All right, or the number of iterations you run within the loop may also change because of the data that you're dealing with. All right, so every instance of a task may also have different timing duration. All right, so that is where we come up with this concept called C, which is worst case execution time. Okay, that means when I look at a task, what is the worst case time? That means looking at the code and all the loops and if else, whatever, what is the maximum amount of time that it may take, okay, the upper limit, okay, of execution. All right, so in this case, of course, the instance tree over here is the worst case execution time, okay, for task 1. And of course, since we are dealing with, we're making the assumption that the tasks are periodic, then we say that the tasks also have a deadline to meet, all right, and the deadline will also have to make sure that it is lesser than or equal to period. Okay, and because of the assumption that the tasks are periodic, we can also say that the deadline must be the period. Correct. When I launch an instance of the task, I know that every period the next instance is going to be released. All right, so I need to make sure that whatever that I'm doing here, I must end before the next instance is released. So the deadline must be equal to the period. Okay, so that is again another parameter that we need to look at, that the deadline, the computation time must be lesser than or equal to the deadline, and the deadline is of course lesser than or equal to the period. Okay, and the additional assumptions here is the tasks are independent of each other. All right, that means when one task is running, it is not dependent on other task. Okay, so it's not like waiting for a mutex or a semaphore or anything. It is able to run independently, okay, regardless of what other tasks are doing. Okay, and we also do not factor in the scheduling, the context switching time, all right, that happens or that is incurred whenever a task switches out. Okay, so then it comes to the another thing, which is worst case response time. All right, so what is worst case response time? Worst case response time here is the maximum elapsed time between the release of a task instance and its completion. Okay, so what is the difference between worst case response time and worst case execution time? The response time factors in the sort of preemption or interference from other tasks. All right, so in this case, I just look at worst case execution time. Okay, so there is no preemption here. Okay, that means when a task runs, it runs to conclusion. Whereas in the worst case response time, we know that there is a possibility that a higher priority task or some other task may take over the CPU. All right, then your current task gets delayed further. Okay, so that is the worst case response time. If you factor in the interference, okay, the other tasks may introduce. Okay, so if you have too much of interference, okay, so for example, over here, task 1 is running, but another task Y comes in and it takes too much time. All right, so by the time the task 1 can resume, okay, and complete, the period or the deadline has already elapsed. Okay, so that is a case where you have missed the deadline because of the interference from another task. Okay, and why this is important? Because in a real-time operating system, we are dealing with what we call the preemptive priority driven scheduling. Okay, that means the moment you have a task that is higher priority becoming ready, that will automatically preempt the current task and take over the CPU. Okay, so that is something that is always happening, okay, in the real-time operating system. So once you have a higher priority task that is ready, it will immediately take over the CPU. Okay, the context switch will happen. Okay, so now let's look at an example of the context switch happening. So I have three tasks over here: T1, T2, and T3. So T1 is high priority, T2 is medium, and T3 is low. Okay, so when T2 is ready at t equals to 0. Okay, so in this case, we are assuming that at time t equals to 0, T2 is initially ready. Okay, so the other tasks are not ready yet. Okay, so when T2 is ready, T2 can run and use the CPU. Okay, and at time t equals to 15, okay, there is another higher priority task T1 that becomes ready. Okay, again, this could be because it was suddenly allocated that semaphore, okay, or the mutex was now available, okay, and now it is now in the ready state. So once it becomes ready, there will be a preemption and T1 will take over. Okay, if anytime again during this period T3 becomes ready, okay, it still has no chance of using the CPU, okay, because T3 is the lowest priority over here. So since T3 is the lowest priority, it has to wait until everybody above it finishes. Okay, so when T1 completes, okay, so at this point of time, something happens, correct? So either T1 completes, okay, or it gets blocked, okay, something happens that allows it to release the CPU. Okay, so the scheduler again will come back and will look that, okay, at this point of time, who do I have? I have T2 and I have T3. Both of them are in the ready state. Okay, but since T2 is higher priority, I will select T2 to take over the CPU. And I eventually, when a point of time when T2 either completes, okay, or gets blocked, okay, and T1 also does not is still in the block state or doesn't need the CPU, then T3 will get a chance to run. Okay, so at this point of time, only T3 is available. So T3 will get a chance to run. Okay, so that is how the priority-driven scheduling works. Okay, and that is basically how a real-time policy is supposed to be, correct? The whole idea of when you say it's real-time is we want to focus on the tasks that need urgent or immediate attention and give it that CPU time. All right, so since priority is so important, how do I assign this priority number? All right, so there are two sort of approaches. One is fixed priority, okay, where the priority does not change with time, okay, and the other one is dynamic priority. All right, so in dynamic priority, the OS may sort of consistently adjust the priority level based on what is happening. Okay, so we will look at one example later on. Okay, so let's look at the fixed priority mechanism first. Okay, so one of the most popular algorithms is what we call the RMS algorithm. Okay, rate monotonic scheduling. Okay, it's quite an old policy, but it's still widely used today to sort of understand how the multiple tasks actually sort of come together. All right, so we say that we have fixed priority assignments, okay, in periodic tasks, and the priority is inversely proportional to task period. Okay, so the smaller the period, the higher the priority. Okay, and the thinking is very simple. If the task period is very small, that means I require frequent attention by the CPU. So if I require frequent attention by the CPU, then I should give it a higher priority so that the moment it happens, I'm able to quickly attend to it, okay, before the next time it triggers. All right, so that is the thinking behind this RMS algorithm. Okay, so let's look at an example of RMS. Okay, so here I have three tasks. Okay, T1, T2, and T3. Okay, so as you can see, we will make the decision on who has higher priority looking at this number here, the period, okay, or which is also the deadline. So the highest priority goes to the smallest period. So this is considered the highest priority, T2. Okay, and then followed by T1 and then followed by T3. All right, so this is following the RMS sort of policy. So at time t equals to 0, all the tasks are ready. So what we will do is, since T2 has the highest priority, T2 will take the CPU first. All right, but T2 only has a computation time of 1 unit. Okay, a computation of 1 unit. So once it is done, it will be able to free up the CPU, okay, until the next iteration, which is at a period of 4 units. Okay, so during that time, the CPU is free. So T1, the next priority, which is medium priority, T1 will get a chance to run. So when T1 runs, it again consumes 2 units of time. Okay, and after that, then T3 will get a chance to run. Okay, so when T3 gets a chance to run, T3 requires 2 units. All right, but because the next iteration of T2 happens every 4 clock cycles, at time t equals to 4, it will get preempted. Okay, so T3 will get preempted and T2 will take over the CPU. Okay, once it is done, it is just nice for the next iteration of T1. Okay, so again, T1 will run, it will take 2 units of time. Following that, then T3 can carry on. So this is actually part of the same iteration. Okay, but it just took, we had to break it up into 2 separate cycles, okay, because of the preemption. All right, then after that, what happens? Then again, the cycle continues. Okay, so after that, at t equals to 8, again T2, then T1. Okay, so now there is no longer any T3 because T3 has already completed, and the next iteration is only over here. Okay, so it's now only between T1 and T2. So T2 runs again, and then at the next time t equals to 15, what happens? When T1 is running, a similar thing happens. T1 only completes 1 cycle or 1 clock cycle of it, but before I can complete the next clock, the preemption comes in from task T2. Okay, so T2 will take over, and then it will be able to go back to T1 and finish off. Okay, and then it sort of repeats, the whole process repeats itself. Okay, so you can see that if you draw it out, okay, in this sort of a time analysis approach, you can see that within the 20 seconds or 20 units of time, the entire sequence is being mapped out. And subsequently, what do you see? That this here is actually very similar to how we started here. Right, this beginning, okay, of time of the behavior at time t equals to 20 is exactly how we started at t equals to 0. Okay, so the whole pattern is now going to repeat. Alright, so that is what we call the hyper period. That means if you can figure out, once you know the hyper period, then the whole cycle repeats itself every hyper period. Okay, what is the hyper period? It is nothing more than the LCM, the least common multiple of the task periods. Okay, so once you know the task periods, you just look at the LCM, okay, and that is the hyper period. And why is this important? Because if I can look at it in one hyper period and I see that I do not miss any deadline. Okay, so if we look back here, you can see that within that one hyper period, I do not miss any deadline. I can make sure that all the tasks can schedule correctly within the deadline. All right, so if I can observe that in one hyper period, then I know that the task set is schedulable because the hyper period keeps repeating itself. All right, so there is no issue in me sticking with this approach and running my task set. All right, so of course, this is the analysis we look at by drawing out, okay, all these clock cycles that the tasks consume. All right, but this is not so practical, okay, or feasible when you have so many tasks and draw it out, okay, over so much of blocks is quite a tedious effort. All right, so the other way is now we look at it from the sort of mathematical analysis. All right, so let's look at some of the algorithms or approaches here. So the first terminology is what we call a feasible schedule. Okay, so a feasible schedule. So if you say that a task set has a feasible schedule, that means we say that I have the ability to schedule all the tasks such that I can meet all the timing requirements, okay, all the timing constraints. Okay, and the optimal scheduling algorithm is one that is able to produce a feasible schedule. Okay, so what we want is we want a schedule where all the tasks can fulfill the deadline. Okay, and the optimal scheduling algorithm is the algorithm that allows me to achieve that. Okay, so let's look at it on how we can do it. And one of the things is the RMS itself, okay, is considered an optimal fixed priority scheduling. Okay, that means if I look at this task, okay, so if I look at this example here, I have 3 tasks. Okay, and if I just look at all the possible combinations of assigning high, medium, and low, okay, across all these different tasks, and I draw out the timing chart, okay, and look at how the behavior in the hyper period, okay, there is a chance that I may find 1 or 2 or more of them that are actually possible to use. Okay, that means in this example, okay, let's assume that maybe I find this and this as 2 possible assignments that actually work. That means I look at the hyper period and I can say that I do not miss any deadline. Correct. So if I'm able to find at least 1 or more than 1, all right, what we can say is one of them is guaranteed to be RMS. Okay, because if you are able to use a fixed priority scheduling and have a feasible schedule, okay, for your task set, okay, one of the possible solutions is guaranteed to be RMS. Okay, and since we know that one of them is guaranteed to be RMS, we can actually start off by using RMS itself, okay, instead of doing some trial and error or doing any analysis. Okay, so we straight away can say that if there is such a task set that exists, then RMS is definitely going to be one of those options. Okay, so that is the thing about RMS. So let's look at the analysis first. Okay, before we even look at RMS, okay, because RMS just tells us that we are going to assign priority based on the period. All right, but first of all, we need to know whether is it even possible for me to schedule all my tasks, okay, with the current computation workload that is required and the deadlines that I have to meet. Okay, so we need to first do some analysis, okay, of the current information of the task set that we have. Okay, so that is what we call the schedulability analysis. Okay, so what you want to do is we want to analyze the system, okay, looking at the worst case behavior, okay, to see whether if I apply this algorithm, okay, what are the timing constraints that are in place, whether I can meet them or not. Okay, so the first thing that we look at, okay, is the schedulability. Okay, so what we need to do is just look at what is the worst case execution time and the period. Okay, so this gives me what we call the utilization, okay, which is the summation of the computation time over the period. Okay, so this gives me a number that sort of tells me the sort of fraction of the processor time that is actually utilized by my code. Okay, so if I look at this task set, okay, if I compute the utilization, I get a 0.75. That means I'm using 75% of my processor time, okay, to run these 3 tasks. Okay, so it sort of tells you that if I keep on adding more and more tasks, okay, where my utilization is higher and higher, then eventually there may be a point of time where this utilization might be bigger than 1. Okay, once it becomes bigger than 1, then we say that it is no longer possible to schedule because 1 is the maximum. That means that is 100% of the processor time. Okay, so that is why the utilization less than or equal to 1 is necessary. Okay, is necessary. That means the moment I say the utilization is greater than 1, then you know for a fact that not schedulable. Okay, that means there's no way that no matter what kind of policy I put in place, it is still not going to be schedulable. That means I need more computing power. Correct. The current system, okay, is not able to handle the workload that I'm trying to run on it. Okay, so it's not possible. Okay, so utilization must be lesser than or equal to 1. So this is a necessary condition. Okay, so then, okay, so this is sort of the English terminology which we must be familiar with. So there's one thing called necessary, but there's also one thing called sufficient. All right. So even though u is less than or equal to 1, is necessary, but it is not sufficient. That means it is not enough to say that just because I fulfill this condition doesn't mean I can schedule it without missing any deadlines. Okay, so that is important to understand. Sufficient condition means that if I am able to fulfill a sufficient condition, that means there is a schedule that exists. But necessary means that is the first level of check. Okay, if the first level of check already failed, then you don't need to do anything else. Okay, because you know it's not possible. Okay, but utilization lesser than equals to 1. Okay, you pass the first level. Now the next level is you must look for some sufficient condition. Okay, so this is not sufficient yet. Okay, you still need to look at other conditions or other checks. All right, so let's look at an example, okay, where we say that utilization is lesser than 1, okay, but yet it may not be schedulable. Yeah, so let's look at these two tasks over here, T1 and T2. So you can see that if I follow RMS, okay, that means T1 is a shorter period, okay, so T1 is higher priority, so T1 runs first, followed by T2. Okay, now what happens? Your T1 will preempt T2 before it can complete. Okay, because T2 requires 4 cycles here. But before T2 can complete, I will have to preempt. Okay, and because the period is 5. Okay, so once I preempt and I run, when T2 resumes, it already passed the deadline. It already passed the deadline. So T2 has missed the deadline over here. Okay, so this is an example of showing you that I'm using RMS, okay, but yet I can still miss my deadline. Because RMS does not guarantee the deadlines. It is just a scheduling policy, okay, and it tells us that if there is a policy, if there's a way to schedule it under fixed priority, then RMS will definitely be one of it. Okay, but now we do not know yet. All right. So you can see in this example, I follow RMS, but yet I'm not able to schedule it. Okay. The next one is, let's say I try the other option, T2 followed by T1. Okay, that means I schedule T2 first, okay, and I follow T1. If I do that, then T1 misses the deadline because T1 is supposed to complete by 5 units, okay, but by the 5th unit, I'm only halfway through the first instance of T1. Okay, so you can see that I'm not able to fulfill the deadline, even though my utilization is less than 1. Okay, even though my utilization is less than 1, I'm still not able to fulfill this ability to schedule both the tasks without missing any deadline. Okay. So a task may or may not be schedulable under fixed priority, even if utilization is less than 1. Okay. Okay, so a task set may or may not be schedulable under fixed priority, even if utilization is less than or equal to 1. All right. So what we now need to do is we need to analyze it in a sort of 3-step process. So first we assign priorities according to RMS. All right. Then we can simulate the schedule for hyper period. All right. And then if no deadline is missed in the hyper period, then we say task set is schedulable. All right. Otherwise, we say it is not schedulable. Okay. So let's look at this. So we can see that if I take these 2 tasks, all right, and like what we did just now, RMS is schedulable. Okay. So RMS schedule is what we have chosen over here, where T1 is considered a higher priority because it has a lower period, followed by T2. And I draw out the time schedule. Okay, and as you can see, within that time schedule, okay, I can already see that I'm not able to fulfill the deadline. Correct. So you already know that within the hyper period, if I cannot fulfill the deadline, then the task set is not schedulable. Okay, then what are the other ways in which I can analyze this? Okay, so then we have another parameter here, which is basically what we call the utilization bound. Okay, so this one is what we call a sufficient condition, but it is not necessary. Okay, it's not necessary. That means even though I don't fulfill this condition, I may still be able to schedule all my tasks. All right, but if I'm able to fulfill this criteria, then I immediately can say that it is schedulable. Okay, and this utilization bound is calculated using this formula over here, where n is the number of tasks in my system. Okay, so this already gives you, this table gives you all the numbers already calculated using this formula over here. All right, and let's look at what we mean by it being sufficient but not necessary. All right, so if I take this example over here where I have these two tasks, T1 and T2. Okay, both having a computation of one in the period of 2, one in the period of 3. If I compute the utilization, so the utilization just now we saw is the computation time over the worst case execution time. Okay, the summation of it. So if I take that, okay, and the utilization is considered, gives me a value of 0.8333. Okay, but since I only have two tasks, okay, for n equals to 2, I get a value of 0.828. Okay, so in this example, my utilization, okay, is bigger than my bound. Okay, utilization is actually bigger than my bound. All right, but if I want to draw out the timing blocks, okay, you can see that I'm able to fulfill the deadline. Okay, because every 2 units is where I supposed to have the task 1, and every 3 units is where I supposed to have task 2. All right, and I have no issue with fulfilling the deadline, okay, for both the tasks. Okay, so you can see that this is an example to show that the utilization bound is a sufficient condition. That means if I'm in a situation where I calculate the u and my u is lesser than or equal to the bound, then straight away I can say it's confirmed that I can have a scheduling approach that will work. Okay, but if I do not fulfill this, it may still be possible. Okay, so I think this sort of gives us a good summary of that. Okay, so the first thing is if the utilization is bigger than 1, you can say for sure that it is not schedulable. Okay, if the utilization is less than or equal to 1, is necessary. Okay, that is a necessary step, but it still does not guarantee yet. It may or may not be schedulable. Okay, but if my utilization is lesser than my utilization bound, then it is sufficient. That means if I already fulfill this condition, then I know for a fact that it is schedulable. Okay. Okay, so now let's look at this, okay, which is called the RMA, okay, rate monotonic analysis, okay, which is a way of analyzing, okay, the task set that meet the necessary condition, but not the sufficient condition. Okay, so the necessary condition is what? That means the utilization is lesser than or equal to 1, but not the sufficient condition. That means it does not fulfill the utilization bound. All right, so this is where we look at the schedulability analysis. Okay, so let's look at this. Okay, example. So I have 3 tasks over here: T1, T2, and T3. Okay, with different computation time and different periods. Okay. Now, if I look at the utilization bound for all the 3 tasks together, okay, the utilization is definitely greater than the bound. Okay, because the bound value for 3 tasks is 0.779. Whereas this utilization, if I calculate, is 0.952. So we can already see that it does not meet the sufficient condition. But the utilization itself, 0.952 is lesser than 1. So it meets the necessary condition. Okay, so necessary condition has been met, but it cannot fulfill the sufficient condition. All right, so now let's look at it step by step. Okay, so let's assume that now I only have task 1. Okay, if I only have task 1, okay, and I compute my utilization and I compare it against the bound, okay, there is no problem. My utilization is lesser than the bound. So no problem. So if I only have task 1 in the system, then I can guarantee that it's schedulable. How about if I add in task 2? Task 1 and task 2 together. Again, I see that the utilization is lesser than about. Okay, that means if my system is now reduced to just task 1 and task 2, I have no issue to say that I can guarantee the schedulability. But the moment I edit all 3 tasks, okay, I edit the third task, and I have all 3 tasks, then I fail the utilization test. Okay, that means utilization is greater than the utilization bound. Okay, so now though you fail the utilization bound test, okay, we know that it may still be schedulable, correct? So that is why we need to look at this concept of what we call the critical instance. Okay, so what is the critical instance? The critical instance is basically a point of time where when I release the task at that point of time, I will produce the largest response. Okay, so when does this happen? It will happen if I happen to release my task together with all the higher priority tasks. Okay, so let's look at this. Now imagine that I have 4 tasks, P1, P2, P3, P4. So this is the highest priority, medium 1, medium 2, and this is the lowest priority. Okay, so as you can see at this point of time here, all the 4 tasks are released at the same time. That means all 4 become ready at the same time. Then what happens? Because of all the higher priority tasks consistently doing their own context switching and running and so on, okay, the task P4 will get very little time to use the processor. Okay, so that is what we call the critical instance. That means I release the task at a point of time where a lot of other high priority tasks are also already in the system or also released at the same time. Okay, so that is the critical instance. All right, so that is what we need to analyze, okay, for our example here. So the critical instance in our case is when all of them are released at the same time. Okay, because I have 3 tasks, one is higher, medium, and the third one is the low priority. So I want to analyze it from this critical instance perspective to understand whether I can still fulfill the schedulable or fulfill the scheduling requirements. Okay, so what we need to do for the critical instance analysis. Okay, we look at the worst case response time for a particular task. Okay, and what we want to do is we want to look at the maximum number of task instances that may release, okay, for the higher priority tasks. Okay, and then we look at whether the overall computational demands, okay, from the higher priority tasks is going to how it's going to interfere with the current lower priority tasks. Okay, so I think if you look at an example, we get a better idea. Okay, so what we have is we know we have 3 tasks, okay, with these 3 parameters here. Now let's look at what is going to happen. So we know that we are interested in actually the response time computation of task 3 because when we added task 3 inside only, we failed the utilization bound. Okay, so what is the deadline of task 3? The deadline of task 3 is the period which is 350. Correct. So we know that in this deadline, okay, we're gonna come back here. How many instances, what I need to look at is how many instances of the higher priority tasks have already been released into the system. Okay, so this is the first instance, second instance, third instance, and fourth instance. So for task 1, I have 4 instances being released, okay, because the period is 100. Okay, so at time 0, 100, sorry, 100, 200, and 300. Okay, so I have 4 instances being released. For task 2, it's the same thing. I have 1. Okay, then this is 150. This is the second one, and this is at 300. This is the third one. Okay, for task 3, I have only 1. Okay, being released. Okay, so as you can see, what is happening is at that critical instance, okay, what is happening is while task 3 is trying to make use of the CPU, I already within that deadline, okay, of 350, I have to also make time for 4 instances of task 1 and 3 instances of task 2. Okay, so those are the interfering tasks that are going to affect my timing for task 3. Okay, so now if I put that into my calculation for interference, so I have 4 instances of task 4 and 3 instances of task 2. All right, that gives me a total interference of 280. So this is the amount of time that all the higher priority tasks need. Now, how much does my own task 3 need? My own task 3 requires 100 units of time, right? The total is 280 plus 100. So total time I need is actually 380. And 380 is beyond the period of task 3. Okay, so if you look at these numbers, you can say that based on this, the worst case response time. Okay, if you remember, the worst case response time means we look at the current task execution time plus all the interference that can happen. So in this case, because there's so much of interference, okay, from higher priority tasks, we are unable to complete task 3 before its deadline. Okay, now when you look at these numbers, of course, the thinking is that task 3 is not schedulable. Okay, so but is it really not schedulable? Okay, or is there something else that we can look at? Okay, so that is where we need to look at a more practical schedule for task 3. All right, why? Because we are now looking at, when we did this analysis just now, we just looked at how many instances of each task were released into the system. Okay, but a more practical approach would be looking at all the instances of time where the CPU was actually free. All right, so if you look at this, task 1, okay, at this point of time, all the 3 tasks are valid. So task 1 is going to take 40 units. Okay, and after that, another 40 units by task 2. Okay, and task 1 is only going to repeat itself every 100 units. Okay, which means that when task 2 finishes at 80 to 100 here, I have a free slot. All right, which means that the task 3 can actually make use of the CPU and do some work during the small gap of time here. Okay, and the same thing over here. When the second iteration of task 1 is done, I finish 140, but task 2 second iteration happens only 150. Which means I have another small block here of time. Okay, and when task 2 finishes at 200, 190, the next iteration of task 1 happens at 200. So I have another 10 units of time here. Okay, and when task 1 finishes over here at 240, okay, the next iteration is at 300, which means I have another 60 units of time here. Okay, and if I add up all of this, I actually get 100. Okay, which is what my task 3 needs. Okay, so if you dive a bit deeper, we can actually see that those small pockets of time, okay, where the CPU was free, was actually enough for me to complete the task 3 within the deadline. Okay, so it is schedulable. All right, so what we now need to do, okay, so that means this earlier critical instance analysis by just looking at the actual interference values alone is not sufficient. Okay, so what we need to do is we need to look at so the problem with the earlier example is we looked at all instances of time where the task was released, okay, within that deadline. Okay, so instead of looking at all the instances of those time, we need to look at all the individual periods, okay, where the higher priority tasks are actually being released. Okay, so we need to look at each time slot. Okay, so earlier on, what we do was we look at the deadline of 350. So based on the deadline of 350, we say that 4 instances of T1 and 3 instances of T2 were released. Okay, so that is how we calculated the interference. Okay, but what we need to do is we need to look at it at all the intervals where all the higher priority tasks are being released into the system. Okay, so that means I need to look at 100, 150, 200, 300, 350, and so on. That means all the periodic intervals of the higher priority tasks. And at each of them, we need to look at what is the demand, that means what is the computational requirement, and what is the capacity, okay, that is available at that time. Okay, so if you look at this, all right, what can we see? We can see that at time t equals to 100, okay, what happens is I have a total demand of T1 and T2 and T3. Okay, this is a T1, T2, and T3. Okay, and that time requirement, computation requirement is 180, but the time that is elapsed so far is only 100. So I'm not able to fulfill yet. Okay, and I do the same analysis. At time 150, what happens? I already have a second instance of T1 being released. Okay, so then I add on here, and then I can see that at each instance of time, what I do is I look at how many instances are being released, okay, and whether that computation time is greater than the current capacity. And what you will observe is at time t equals to 300, I have actually 3 units of T1, 2 units of T2, and 1 unit of T3. And if I add up all of that, I will see that the total demand is 300 and the amount of time elapsed is also 300. Okay, that means if I look at the 300 as the deadline, okay, where I look at all the instances of the higher priority tasks, then I'm actually able to fulfill the timing requirements of task 3. Okay, so of course, doing this manually like this is tedious, correct? So that is why we have a better approach, okay, which is the next schedulability test. Okay, so that test here, okay, basically computes both the necessary and basically by looking at this, you can ensure that you have the necessary and sufficient condition, okay, for the task set that you want to schedule. Okay, so instead of going through all of these numbers, okay, I will look at it from the example, okay, and I think it's easier for us to see. And what you need to do is, okay, you need to compute, okay, the instances, all right, where the tasks or the higher priority tasks are repeating themselves. Okay, so in this case, the instances will be that time equals to 100, 200, 300 for T1, 150, 300, and 350 for T3. Okay, and basically what you need to do is you just compute this parameter, okay, for each of those periods. Okay, and what you do is for each of them, you compute based on the computation time C. Okay, and this is the ceiling, which is the current time value here, which is the T, over the period of that particular task, and you take the ceiling of it. Okay, so you do this for each task. So this is for task 1, okay, task 2, and task 3. Okay, and what you do is you see whether the computational requirement at that particular time is lesser than or equal to the actual time already elapsed. Okay, if that condition is true, then we say that this is a necessary and sufficient condition for schedulability. Okay, that means we are able to say that right now that this task set is schedulable, okay, by following the priority assignment we have done. Okay, so this is the sort of the best way to finalize that this is schedulable. All right, again, do we need to come to this stage, okay, to know whether it's schedulable? Not necessary, because if your utilization bound was already successful, okay, earlier on you already do a calculation and you already fulfill the utilization bound, then you do not need to come onto this, correct? But if your utilization bound fails, correct, and then you want to check for the necessary and sufficient condition at the same time, then this is what you can do. Okay, you can come and perform this analysis. But when you do this analysis, you must look at all the periodic intervals of the higher priority tasks and do this computation. Okay, and if you're able to reach a point of time where the total computational requirement is lesser than equal to the time that is elapsed, then you have fulfilled the condition. That means you can say that this task set is schedulable. Okay. Okay, so I know there are quite a few numbers and formulas and all, but once you look through again and you look at it, it's not so difficult. Okay, it's quite straightforward. Okay, so let me just finish this off. There's only about 2 more slides, okay, before we go for a break. Okay, so until now, okay, when we looked at RMS and everything, we were looking at the sort of fixed scheduling policy. Okay, that means once, fixed priority scheduling policy. That means once you have already assigned the priority level, that priority stays with it throughout the whole system, throughout the whole time when the system is operating. All right. The other alternative is a dynamic priority scheduling system. All right, where the priority is constantly changing. Okay, and one such scheduling is what you call the EDF. That means the earliest deadline first scheduling. Okay, that means the task with the earliest deadline will always be given the highest priority. Okay, so what the system will do is it will look at the current deadline of all the active tasks. Okay, and as and when a new task instance is released, it will decide whether the current task and this new task, what should be the priority levels. Okay, so it is a dynamic, like on the fly decision. All right, so let's look at example. Okay, and we sort of see how it works. So currently I have 2 tasks, T1 and T2. And since task 1 has a earlier deadline than task 2, so task 1 will initially be given the high priority. So task 1 will run first. Okay, so task 1 will run for 2 units. Okay, and after that, okay, task 2 will run. So we assume that both the tasks are released at the same time at time t equals to 0. So over here T1 and T2 are released. Okay, so but since T2's deadline is further away, okay, at time t equals to 0, T1 has a higher priority, so T1 will run first. Okay, when T1 runs, then after that T2 will run. Okay, and every 4 units of time, T1 will repeat. Correct? So T1 will have to repeat itself here. Okay, but now let's look at what happens over here. Okay, over here, what happens? T2 is running. Okay, when T2 is running, okay, T2 requires 5 units of time. Okay, T2 requires 5 units of time. Now, the priority again, if you look back here, the priority is updated when a new task instance is released. Okay, so what happened here is a new task instance is released at this time. So whenever a new task instance is released, you will look at the deadline. So at this point of time here, okay, at this point of time, what happens? You will see that I have task 1 being released and task 2 is still there. But whose deadline is going to come earlier? Okay, task 1's deadline is going to come earlier. All right, because task 1's deadline is over here. Whereas task 2's deadline is over here. All right, so because task 1's deadline is coming earlier, task 1 will be given a higher priority to run first. Okay, so task 1 will run, okay, with a higher priority, and then task 2 will continue. So as task 2 is continuing, you can see again at this point of time what is happening. At this point of time, another instance of task 1 is released. Okay, but at this instance of time, when time t equals to 8, T2's deadline is at 10, 2 units away, whereas T1's deadline is 4 units away. So that is why even though task 1 is released, okay, at time t equals to 8, okay, it does not get to run yet. Okay, task 2 will still continue to run until it finishes. Okay, then T1 will get a chance to run. So when T1 is running, again the same thing. At time t equals to 10, I have another instance of T2 being released. Okay, but again, T2's deadline is far away at 20. Okay, T1's instance is deadline is earlier, so T1 will be given a higher priority to continue. After that, then T2 will run. Okay, so again, the same thing happens. All right, at time t equals to 12, another instance of T1 is released. Okay, and since T1's deadline is 4 units away, whereas T2's deadline is, okay, at time t equals to 20, you still have give higher priority to T1. So T1 will run, and then at that time T2 will run. Okay. Now at this point of time, you can see that T2's deadline is at time t equals to 20, and T1's deadline is also at t equals to 20. So both of them now have the same priority because they are both having the same deadline, which is 4 units away. So if they are both having the same deadline, then the current task will still carry on. Okay, and then the next task will take over. Okay, so in EDF, basically what is happening is the priority keeps updating itself as and when the a new instance of a task is released. Okay, so EDF is a optimal scheduling policy. Okay, so one thing about EDF is as long as the utilization is lesser than or equal to 1, okay, it is possible to produce a feasible schedule. All right, so that is the good thing about this. Okay, so of course, again, this is more complicated to sort of develop at the OS level. All right, whereas a fixed priority system is more easier. Okay, so that is the EDF optimality. Okay, so we have come to the end of this chapter, all right, where we have looked at various scheduling policies. Okay, and we spent quite a bit of time in the RMS. Okay, and the EDF just to give you the idea of how the dynamic priority scheduling works. Okay, so again, I think it's more theoretical. We make some assumptions, okay, because we need to sort of understand the concept behind it. Okay, but in reality, of course, some of these assumptions may hold true, some may not. Okay, and in terms of the calculations, okay, I think it's also fairly easy, not too complicated. All right, so when you go through it one more time, then you will see it's quite easy to apply those formulas and calculate the numbers. Okay, so what we will do now, we will go for a break. Okay, when you come back from the break, I will talk to you about the midterms. Okay, and then we'll look at the lab demo. Okay, so let's go for a 10 minutes break now. Okay, then I'll come back and talk to you. Okay, so let's carry on. Okay, so let me share this first about the midterm next week. Okay, so firstly, make sure you have gone through the instruction document that I've uploaded. All right, so that gives you all the details about the timing, okay, and the setup that you need. All right, I think all of you have done online Luminous quiz before, so you should know the procedure quite well. Okay, screen recording and Zoom proctoring, please make sure you test it out on your own. All right, especially the screen recording. Okay, you need to make sure that it is able to last for at least about 45 minutes. The test itself is 40 minutes. Okay, so you need to make sure that you have enough storage in your system to make sure that you can record for at least about 45 to 50 minutes. All right, so test out the software. Okay, make sure that everything is recording correctly in the screen and so on. Okay, sometimes if your settings are not correct, you think it's recording the screen, but maybe it's recording your webcam, okay, or something else. Okay, so you need to make sure that everything is tested beforehand. The Zoom proctoring, again, you need to set up your phone, okay, to make sure that the invigilators can have a clear view of you and the screen and so on. Okay, so all this, I think you should be familiar. Okay, so just make sure you do that. Okay, so it's open book, which means you can refer to our course material and data sheets. Okay, you're not allowed to do any online searching for answers. Okay, and you're not allowed to access any form of coding platform. Okay, whether it's online or on your laptop or whatever. Okay, so those two things are not allowed. All right. The other thing is the LED behavior. Okay. Okay. No code platform means you can't use microvision. Yeah, you can't access microvision to see your codes. Okay, from previous labs. Okay, so whatever that you want to keep a copy of, okay, your code that you have written, whatever, you can create some PDF out of it and just access it as a document. Okay, so if you want to access your code that you have written before, yes, you can just create some PDF or Word document where you copy everything. Okay, but you're not allowed to open any tool that can allow you to write code or test code or anything like that. All right. Another important thing is LED behavior. Okay, so even if you look at the past year, midterm, and so on, there's always questions on what is the LED behavior after this, or when I run this code and so on. So the LED behavior is basically how I have been demonstrating in the lectures. All right, because some of you, when you write your own LED code, that behavior might be different. So like for one thing is, when I say LED red on or red off means I only control that LED, but I do not affect the other colors. Correct? When I say red LED on means if the green is already on, the green will still stay on. Correct? I do not switch off the other colors when I on my red LED. Okay, so that is how my code is written, and that is how you're supposed to look at the questions in the midterm. Okay, so it is all based on how I have been demonstrating, okay, in the lectures. All right, the RTOS is always, okay, with default settings unless it is mentioned otherwise in the question. All right, and the default setting means round robin is enabled and all tasks are created with equal priority. So these are the default settings, okay, in which the RTOS questions will be based on, unless it is mentioned. All right, that means if there's a particular question where I say that round robin is disabled for this question, then that question alone you look at it differently. Okay, or if one of the question the task has a different priority than the other task, then that applies to that particular question. All right. Okay, so again, you need to make sure you look through all the instructions, everything carefully. Okay, as always, there will be people who come and ask me what is default settings during the midterm. All right, and if they ask me during the midterm, I will just say no comment. Okay, so because it has already been mentioned in today's lecture, okay, and I'll also send an announcement on it later. Okay, so anything that has already been announced to you all earlier, okay, in any form, either lectures, announcements, or instruction document, okay, it means that I've already informed you all. Okay, so please make sure you are up to date and you know what is happening. All right. Yeah, other than that, if you have other clarifications regarding the question that I feel okay, that is maybe not clear or something is not right, then I will definitely clarify in the Google document. All right, so I will be sending an announcement again this week, okay, with all the links, okay, for the Google form and the Google document to make sure you are able to, just make sure you're able to access all of those documents without any issue. All right. Okay. In terms of the format, okay, so there will be MCQ, okay, plus some true/false questions. Okay. Total number of questions will be around either 18 to 20, around that. Okay. So these are total number of questions, or 18 to 20, and MCQ plus true/false. The actual time is 40 minutes. Okay. So the actual duration is 40 minutes for the midterm. Okay, so all of that is already, the timing, everything is mentioned in the instructions document. So please look at that. Okay. So any other questions you have, you can ask me later or you can email me. Then by the end of the week, I'll consolidate whatever questions that I need to clarify, and I'll send another announcement. Okay, so that's about it for the midterm. Okay, so for this week's lab, in this week's lab, we are going to follow up based on the last week's lecture. So last week's lecture, we did both mutex and semaphore. So in last week's lab, we did the mutex. So this week's lab, we're going to do the semaphore. Okay, so if you look at the semaphore, so if you recall, a semaphore is basically another way of managing resources. Okay, and in this first example, okay, what we're going to look at is where I've created a new semaphore. So when you create, when you call OS semaphore new, okay, if you look at the data sheet, okay, you can see that you pass in two parameters, the max count and initial count. The max count is the maximum number of resources you have, and the initial count is where do I start from. Okay, so in this first example here, what I'm doing is I am saying 1 and 1. That means I have one resource and I have one what maximum count is 1, and the number of resources currently available is 1. All right, and then over here I have OS thread new, LED red thread, LED green thread. All right, I created both of them. Now let's look at the code first. Okay, so in this code, what I've done is in each of the thread, I acquire, control, and then release. Okay, acquire, okay, and then I do a control and then I release it. All right, so over here, what do you observe? Okay, okay, maybe we build the code over here. Oh, okay, wait now. Okay, so in this first example here, when we run the code, okay, basically what you observe is you observe the red and green alternating or blinking alternately. All right, so this is similar to the mutex example. Okay, so the sort of flow, okay, the sort of flow is the same. All right, where what is happening is I've created a semaphore. Okay, so in my semaphore, my initial count is 1. All right, so I have my red thread over here. Okay, and I have my green thread over here. Okay, and since red runs first, it will take the semaphore. So it will sem acquire. Okay, when it does sem acquire, what happens? Your semaphore value will become 0. Correct? So when semaphore becomes 0, there are no more resources available. So over here, once I do that, I on the LED and then I call the delay. Okay, so when I call the delay, what happens? I go to a block state. Okay, so from here onwards, I go to a block state. Okay, which means that I'm now able to do a context switch over, and the green, which was all the while in the ready state. So all the while it was in the ready state. Okay, when eventually the red goes to the block, okay, I'm able to run. Okay, when I run, what do? I try to take the SEM acquire. Okay, but what happens? The semaphore value is currently at 0. So when semaphore value is at 0, okay, what happens? I'm not able to continue executing. All right, so I will go to a block state. So after this, I will now go to a block state. Okay, only, and I'll carry on this, correct, until the point of time when this 1 second is finished. Okay, when the 1 second is finished, then I will be able to come out and I will say I will off. Okay, and then I will. So if you look at the code, what is happening is you have to wait until the off, and then I want one more second, and then I release. Correct. So I off, and then I wait another 1 second, which is blocked. So another 1 second, which is blocked over here. Okay, and then finally I release. Okay, I semaphore release. So when I semaphore release, what happens? What happens to the account? Does it become 1? Can anybody tell me what will become a semaphore count? Okay, it is still 0, correct? Okay, why is it still 0? Because there's already somebody waiting in the queue. There's already somebody waiting in the queue. So once it is released, okay, it becomes immediately allocated to semaphore. So the it becomes immediately allocated to the green thread. So green thread becomes unblocked. Okay, it's not going to run yet, okay, but it becomes unblocked, okay, which means it transitions to the ready state. Okay, so the task red thread can still run, okay, but once it goes back to the beginning of the loop, what happens? It tries to do another SEM acquire. Okay, and since there is no resource available, then it goes to the block state. Okay, and since it goes to the block state, it allows your this green thread to run, and then the whole thing repeats. Okay, so the green thread will continue to hold the semaphore until the LED blinking is complete, and once that is done, then it releases the semaphore. Okay, so that is basically the behavior. So in a sense, it's like what we talked about in the lecture. This is what we call a binary semaphore, and a binary semaphore behaves in a similar fashion to mutex. All right, but again, if my intention is to actually control mutual access or mutual exclusive access to the LED as a resource, then I should actually use mutex, okay, for this. Even though semaphore also works, okay, I should be using mutex for this. Now, instead of thinking of just using semaphore as another proxy to mutex, okay, another more interesting application of semaphore is actually to synchronize threats, okay, which is what we're going to look at now. Okay, so how am I going to synchronize the threats? Okay, that means instead of right now, what is happening is the moment I say OS kernel start, what happened? All the threads start running and they just run indefinitely in a loop. Okay, of course, they transition in and out because of the OS delay. Okay, now how can I synchronize the thread to be tied to certain events? Okay, like in your robot, for example, when your robot does something, okay, when it moves a certain distance, then I want the LED to light up, or when the LED light up finish, then I play a sound or something like that. So you want some tasks to maybe synchronize with each other. Okay, so that is one thing that you can achieve with semaphore. All right, so what we're going to do is for OS semaphore view, okay, the maximum count is still 1, but my initial count, I'm going to put it as 0, which means that when my semaphore is first created, there is actually no semaphore available. I've already created it, but initial count is 0. Okay, and what will happen if my initial count is 0? Then when my LED red thread and LED green thread run, what will happen? They will both go to a block state. Correct? Because what will happen? Your LED red thread will go to a block state. Okay, so let's look at this. Okay, so if I look at this next piece of code over here, okay, where my initial count is equals to 0. Okay, so if my initial semaphore count is initialized to 0, when my red runs, what happens? Okay, it will try to do sem acquire, and then there is no acquire, there's no resource, so it will go to a block state. Okay, and once it goes to a block state, I will be able to transition. So my green thread, okay, which was initially in the ready state, will be able to run. And once it runs, it will also try to do a sem acquire. And then since there's no semaphore available, it will also go to a block state. Okay, so if you look at the semaphore queue, okay, so if you look at the semaphore queue, okay, on the tasks that are waiting, initially you have the red thread and then you have the green thread. So both of them are in the queue waiting for the semaphore to be available. All right, so that is what will happen if I make my initial count 0. Okay, so let me okay, so later I'll show you that. So now, how am I going to control the LED, or what is the event that I'm trying to capture? So in your lab, okay, when you're looking at doing the lab, what we're doing is we're going to link this back to the earlier studio with the push button. The earlier lab with the push button. All right. So the configuration of the push button, all of that, you need to make sure you copy over from your, I think, lab 3. All right. So that part all you copy over, and then your port D interrupt handler, basically what it's going to do is, okay, whenever I press the button, okay, I'm going to release a semaphore. Okay, I'm going to release a semaphore. Okay, so this delay I put here is just to bypass the debouncing. Okay, so we know that there is a debouncing, okay, issue. Okay, so the easiest way to just ignore that for the time being is to put in some delay. Okay, so this delay I'm going to put in. What this ARM handler does is this delay, after this delay, I'm going to release a semaphore. Okay, so every time I press a button, I release a semaphore. Okay, so let's just run this code first and observe what is going to happen. Okay. Okay, so now that I'm running, you can see that there is no blinking at all, because as what we saw, both the tasks will be in the block state. All right. So what I'm going to do now is I'm going to press the button. Okay. When I press the button, okay, you can see that the okay, sorry, I forgot to. Okay, so there's one more thing I forgot to do over here. The release, okay, must also happen only through the push button. So the green thread and red thread should not release a semaphore. Okay, they only acquire a semaphore. The release is only done through the IRQ handler. So let me compile this again. Okay, and okay, so this is the correct one. Okay, so initially there is no blinking. When I press the button, okay, the red LED blinks just once. Okay, and if I press one more time, the green LED blinks. Okay, and similarly, every time I press, I alternate between the red and the green. If I don't press, there is no LED. Okay, so that is the behavior you should be expecting in the lab. So what is happening? All right, so while they are both blocked, okay, while they are both blocked over here, okay, we're waiting for some semaphore, all right? So both of them are blocked. So when I press a button, so when the IRQ is triggered, what happened? When I press a button, I release a semaphore. So when I release a semaphore, the first task in the queue, in the semaphore queue, will be allocated as semaphore. So when the first button is pressed, the red is allocated as semaphore, so the red will be able to unblock. Okay, so it will unblock. Okay, so when this happens, it will allocate a semaphore to the red task, it will unblock, and then the whole sequence runs. Correct. So it on, it delay, it off, everything. Okay, then eventually you will look back again. Correct. You will look back to the semaphore acquire, and since there is no semaphore release, you will go back to the block state again. Okay, so this is the whole sequence will happen here. So we'll go back to the block state. Correct. And then the next time another IRQ is triggered, what happened? Okay, so when this event happens over here, what happens is the red joins the queue, but now red is after the green. Correct. Red is now after the green. So when the next interrupt is triggered, then the semaphore is released to the green. So the green now gets the semaphore. So it now goes through the whole sequence, so on everything. Okay. So now you can see that everything is or the sequence is such that the tasks are waiting for some event. And how do you wait for an event? You call for semaphore acquire while there is no semaphore. Okay, so if you try to call semaphore acquire without any semaphore, you go to a block state until somebody releases the semaphore. And in this case, your IRQ handler is the one releasing the semaphore. So the moment I acquire the semaphore, I'm able to run it one time. Okay, because once I acquire, I am able to run my code one time. And then the next iteration of the loop, I wait for the next semaphore and so on. Okay, so that is one of the things you will try in the lab. All right. Of course, later on, I also ask you to integrate this with your earlier code, which is the app. All right, to control the motors and so on. So what you can do is now, instead of using your polling approach and your task, okay, one way in which you can put everything together is such that your app, okay, when you press a button, okay, what will happen is you're going to send some data, okay, to your ESP32, okay, which is now going to send data to your KL25Z. Okay, and now we're going to configure it as interrupt. Okay, so inside your IRQ handler, okay, what you can do is you can, so inside your serial interrupt, then what you do is when your data comes in, based on the data, you do some if check, then for each of those check, what you can do is you can semaphore release. Okay, so each of this can trigger different tasks. So this could be for task moto, this could be for task audio, and so on. Okay, so this is one way in which you can sort of put your code together. All right, but we will be learning other techniques as well. Okay, so right now when you look at using semaphores, you might think that okay, semaphore already is good enough for me to synchronize the whole system, and I can sort of trigger different tasks to do different things, okay, with semaphores. All right. Why? Because once I make sure that, so for each task that I write, the T motor and T audio, whatever, so each task could be written such that they are there, but they are waiting, okay, for the semaphore to be acquired before I do something else. Or I could do something else first and then I wait. Okay, so your task could be written in a way that I do something first, okay, and then I wait at some point for the semaphore before I carry on. Or in the beginning itself, I block until the semaphore comes and then I carry on. Okay, so that is again your design. All right. Again, you'll be learning other mechanisms as well. Okay, so semaphores are of course one way to put things together for your project. Okay, but you'll be learning other things called events and flags. Okay, so those are also very, very useful tools to synchronize and communicate. Okay, and you'll also be learning about message queues. Okay, how we can send data together with synchronization. Right now, what is happening is when I call semaphore, if I use this approach, okay, your task motor or task audio can sort of unblock and carry on. Okay, but I can only unblock and carry on without sending any extra data or extra information. Okay, when we are going to learn about events and flags, okay, we can use events and flags and message queues, okay, as a way of not only synchronizing but also sending data at the same time. So your task motor could get unblocked with some new data coming in at the same time, and then you process the new data. Okay, so that is another way of putting things together as well. All right, so semaphore is one option. All right, but just wait until you finish that chapter as well before you finalize on your strategy on how the whole architecture is going to be. Okay, now before we end, just one more thing. Coming back to this example right now, okay, if I want to just modify this a bit and say that I would like both thread to wake up and light up together every time I press the button one time, what can I do? Okay, currently when I press one button, okay, press the button one time, one thread wakes up. Okay, but with this same sort of architecture, I just want to make sure both the thread wake up together. So I see a yellow color, okay, every time I press the button. Can anybody suggest to me what I can do? Any ideas? Yeah, so the idea is you want to be able to release two semaphores at the same time, right? Because each task is waiting for a semaphore. All right, so if I'm able to release two semaphores at the same time, then I can solve this. Correct. So what I need to do is over here, I must change the max count to 2. Correct. And then what I can do here is I can release this twice. Okay, I can release this 2 times. Okay, so what will happen is when I release it the first time, the first person in the queue will get it, and then immediately I release again. So the next person in the queue will get it. So both the tasks will be able to sort of unblock and start executing. Okay, so let me show you over here. Okay, so again, by default, there is no LED. Now when I press, you see it as yellow. Okay, so basically what is happening is the same thing. Only thing is now that I've released my increased my count to 2, and my interrupt handler is releasing both, okay, one after another. Both the tasks sort of wake up around the same time and are able to control the LED. Okay, so that is basically what is happening. So you can see that with semaphore, okay, because we have this concept of count, all right, we can also increase or decrease the number of semaphores to again wake up multiple threads at the same time. All right, so you can use it for individual threads, you can wake up multiple threads at the same time. So there are a lot of different ways you can do it. Okay, so again, this is just one of the tools you can use. Okay, we are still going to learn events, flags, and message queues. And once you learn all of that, then you can put everything together and decide on architecture. Okay, again, the architecture wise, it's up to you to decide how you want to put them together or what strategy you want to use, okay, in terms of designing your overall code. Okay, and I think that is something that you can do remotely, okay, through a Zoom call with your teammates, everything. The important part is the hardware, okay, making sure that part is sort of settled while you are having lab access. All right, so try to again maximize the lab use, okay, to finish up the hardware as much as possible. These lab exercises you can do on your own, all right, so that you can use the lab time more effectively for the hardware. All right, so that sort of brings us to the end of this week's session. Okay, if you have any things you want to ask, you can stay back and ask. If not, thank you very much. Okay, I will see you all in the lab.